Okay, guys, today we're going to be going through our second lesson of Chapter 2, Properties of Water. So, something to think about. When we travel to outer space and we look at the Earth from space, they said it was a blue, so to say, planet referring to the oceans that cover nearly three-quarters of the Earth's surface. Okay, now, with all this being said, there's something very special about water and the role it plays in living things. Now, what we cover in this lesson is very important to having a basic understanding of chemistry, which we will use in our next two units, ecology and the cell. So we have our first question here that we need to think about. How does the structure of water contribute to its unique properties? So water is one of the few compounds that's found liquid over most of Earth's surface. Now, what this means is that when we look at everything else around us, the chair that you're sitting in, the air that you're breathing, those are all solids or gases. Very few substances are liquid at room temperature. Another example of a substance would be lipids. Okay, so some of our lipids, things like your vegetable oil, canola oil, peanut oil, and also mercury, like you would find in an old thermometer. Now, like other molecules, water is neutral. The positive charges on its 10 protons balance out the 10 negative charges on its 10 electrons. So plus 10 minus 10 gives us a charge of 0. Now, polarity, because of the angle of its charges, we can see we've got our hydrogens down here and our oxygen up here. The oxygen's a lot bigger than this hydrogen. Okay, it gives one end of the molecule a negative region and the other end a positive region. But again, overall, it still remains neutral. Remember, 10 positive, 10 negative, still giving us 0. So there's a greater probability of finding the shared electrons in the water close to the oxygen atom. Because those electrons have a negative charge, we say that the oxygen region is going to be negative, and the hydrogens, therefore, would be positive. Now, a molecule, when this happens, is said to be polar because the molecule is kind of like a magnet with two poles. Okay, so the charges on a polar molecule are written in parentheses, and that way we show that we aren't talking about ions like sodium or chlorine where we've actually gained or lost an electron. We talked about those types of bonds in the first lesson with our ionic bonds. So the question is hydrogen bonding. Now, because of their partial positive and negative charges, polar molecules such as water and our liquid lipids, like I talked about a minute ago, can form hydrogen bonds. So the attraction between a hydrogen atom on one water molecule and the oxygen atom is known as a hydrogen bond. Now, these bonds are incredibly, incredibly weak. We know this because when you put your hand in water and try and pick it up, all of the bonds that are holding those individual water molecules together separate very, very quickly. But it's when we take all of them, millions and millions, if not billions of them, and put them together, they do become pretty strong. I'm sure that summertime when you've gone swimming, you may have had the misfortune of trying to do a somersault off the diving board and you do a belly flop. That sting that you feel when your stomach hits the water is actually going to be all of those bonds, the force holding them together. Your stomach, your face, everything has got to separate those as you enter the water. Okay, so water is able to form up to 4 hydrogen bonds for each water molecule. Okay, so they, like I said, they're not as strong as covalent or ionic bonds, but they can form in other compounds besides water as well. Now, let's talk about cohesion. Now, cohesion is an attractive force between molecules of the same substance. So when you look at a pure substance like pure carbon, like you would find in a diamond, or within water, when we have a water molecule sticking to another water molecule, we call that cohesion. Okay. Now, cohesion causes the water molecules to be drawn together, which is why water droplets will form beads on a smooth surface. It also produces that surface tension I was talking about, why you got to, break that surface tension of water, and that's what makes your stomach burn when you do that belly flop, or what even allows some small insects to be able to walk on a pond's surface. Now, adhesion is an attraction between molecules on different substances. So when you look at a graduated cylinder, you see what's called a meniscus, how it will dip slightly in the middle of the graduated cylinder because the water molecules are actually grabbing onto the sides of the graduated cylinder. Now, In terms of adhesion, this is what we also call adhesives, okay? Just what we commonly refer to as glue. So like Elmer's glue, super glue, those are all adhesives. We use them every day. Ladies, when you go to the nail shop, that insanely strong glue they use, that is a very strong adhesive to put that nail into or onto the fake nail, onto your actual fingernail. Okay, so it also creates what is called capillary action. So capillary action is one of the forces that draws water out of the roots of a plant and up into its stems and leaves. This is all passive. No energy is used for this. Okay, cohesion will hold the column of water together as it rises. So even in the largest of trees, the great sequoia trees and the California redwoods out in the western United States, the tallest trees on the earth, they still move water from the roots all the way to the very top of that tree using no energy at all. Okay, so there's no physical pumping using energy to get that up there. So heat capacity. Now, heat capacity is something that's kind of difficult to understand. But to put it simply, we see that water's heat capacity, the amount of energy required to increase its temperature, is relatively high. Now, you think about when you boil water on the stove at home. Okay, you take, let's say, 2 liters of water, you put it in a pot, you turn on the stove, which uses energy to heat that water up. The amount of energy to do that is relatively high. Okay, now to be specific, heat capacity refers to the amount of energy it takes to increase 1 gram of a substance by 1 degree Celsius. Okay, now at the cellular level, water absorbs a huge amount of heat that's produced by cell processes, which regulates both the temperature of the cell and also of the temperature of our bodies. Now, this explains why when we are hot, when it's outside, in July and August in the South, it's 95 degrees outside, you can easily become dehydrated, meaning that you're losing water because you're sweating. It carries that heat away from your body through that sweat. But unfortunately, if you're not replacing that water, it causes you to get sick pretty quickly. So let's talk about how water functions in solutions and suspensions. How does water's polarity influence its properties as a solvent? Well, water obviously is not always pure. In fact, most of the time it isn't. I would reckon that most of the time that you take water into your body, it's actually in the form of a mixture. Now, a mixture is going to be a material composed of 2 or more elements or compounds that are physically mixed together but not chemically combined. That means we can separate them. So living things are part composed of mixtures involving water, and the 2 types that we're going to talk about are solutions and suspensions. Now, with a solution, okay, this is when we have everything mixing equally. So we have this example of table salt. Now, we have our water molecule. It surrounds our salt crystal right here. And when that happens, it causes the sodium and chlorine ions to separate, and then those are surrounded by water. Now, we say that they dissociate. So they break away from the crystal and are surrounded by water molecules, and we call this a solution when it is evenly mixed throughout the entire substance, in this case, the salt water. Now, all the components of a solution are evenly distributed. That's the important thing. So in the saltwater solution, we have both solutes and solvent. Now, the solute is the substance that is being dissolved. And in this case, water is the solvent. Most of the time when we talk about a solution, the solvent will typically be water. So water's polarity gives it the ability to dissolve both ionic and other polar molecules. We know that when we put sugar into water, when we put Kool-Aid powder into water, all of that, it will separate. However, we'll see that sometimes that it doesn't actually dissolve everything. If you make a pitcher of Kool-Aid or of sweet tea, and any type of sports drink from a powder, and you leave it sitting for long enough, you'll actually notice that it will begin to settle to the bottom. So when a given amount of water has dissolved all the solute it can, the solution is said to be saturated. Just like, if you get caught outside in the pouring rain and your clothes get saturated because they can't hold any more water. Now, sometimes materials don't dissolve when placed in water. Okay, so this forms what is called a suspension when we have water and non-dissolved material together. So if you take Sand, for example, like you would pick up at the beach and you put it into a container with water. You can shake it up and it will mix temporarily, but relatively quickly, all of that is going to actually settle back down to the bottom. And at that point, we have this suspension. That sand is literally suspended in the water. Okay, so some of the most important biological fluids, though, are both solutions and suspension. So blood, for example, that circulates in your body is mainly water. It contains many dissolved compounds, but also cells, other undissolved particles, even some waste products from your body that you're trying to get rid of. Okay, we can take the blood and we can run it through what's called a centrifuge and separate it. I'll talk about that later in chapters 7 and 8. So why is it important for cells to buffer solutions against rapid changes in pH? So we're going to talk about acids, bases, and pH real quick. Now, water molecules sometimes split apart to form hydrogen ions and what are called hydroxide ions. So hydrogen ion is represented by this H+, hydroxide ions represented by this OH-. This reaction can be summarized by this chemical reaction that we see here. And we have these arrows that go both ways. That means that this reaction is reversible. If you take a pure hydrogen ion and pure hydroxide ion and you put them together, they're pretty much going to form a water molecule. So in pure water, about one water molecule in 550 million splits to form ions in this way. Now that is really, really, really small in proportion. 1 out of 550 million. So we highly favor the maintenance of water instead of the separation of it into these two ions. Okay. Now one of the ways around this is through putting a high electrical current through water. That's what Elon Musk is trying to do with Tesla right now. So the pH scale. Now you may need to turn your head sideways to see this, but it ranges from 0 to 14. We have increasingly basic, increasingly acidic over here. A pH of 7 is said to be neutral. That's going to be pure water. So some of the things we can see here that are probably common, we've got, soap right here, like you wash yourself with at home, lemon juice, tomato juice. We're not talking about ketchup, but actual tomato juice, acid rain, stomach acid down here. If you've been eating 3-4 bags of hot fries every day and you get that burning feeling in your throat, that's actually stomach acid coming back up. So you need to kind of neutralize that. Then, on the other end over here, we've got bleach at about 12.5, oven cleaner at 13.5. Very, very, very basic. So solutions with a pH below 7 are called acidic because they have more hydrogen ions than hydroxide ions. The lower the pH, greater the acidity. And then we have the inverse being said for bases. So they're basic because they have more hydroxide ions than hydrogen ions. The higher the pH, the more basic the solution. Each step on the pH scale represents a factor of 10. So this is not a linear scale. It's an exponential scale. So a liter of a solution with a pH of 4 has 10 times as many hydrogen ions as a liter of solution with a pH of 5. Okay, so we can't say that we see right here normal rainfall with a pH of 6. And then we have a pH of 5 for acid rain. It's not twice, it's actually 10 times as acidic. So we've already talked about what an acid is. They contain higher concentrations of these hydrogen ions. We can see examples right here. You'll want to make sure to reference this in your lesson, in your assignment as well. Okay, and we see the same with our base right here. So this right here has our actual definitions that I would like for you to use for acids and bases. Now, the question is, how do we buffer these? Okay, we want to not have these huge changes in pH within our body. Okay, so we want to keep most of the body between a pH of 6.5 and 7.5 to maintain homeostasis. Now, if the pH is lower or higher, it'll affect the chemical reactions that will take place, and we use buffers to help do that. Okay, so adding acids to an unbuffered solution causes the pH to change drastically. However, if you add the acid, if it contains this buffer that can help neutralize that, it will only cause a slight change in pH. Okay, so I invite you to read your book, section 2.2, to read up more on buffers to have a better understanding of how they function. If you have any questions, please make sure to post in the comments below, or you can send an email to mr.tucker.schs@gmail.com. Now, I want to turn to our assignment quickly and look at a couple of the questions specifically that you guys may have a little bit of trouble doing in Google Docs. Okay, so I want to look at this table right here first. Okay, so you can very easily just click and type in this. That shouldn't be a problem at all. But I want to come down here and make sure that you read the directions carefully. Now it says on the pH scale, indicate which direction is increasingly acidic and which is increasingly basic. Okay, so you can use Google Docs to draw an arrow on this, or you could probably just type on it as well and label which side is acidic or basic.